Okay, we're going to talk about 5.4, number 16. Before that, we're going to talk about these work problems in general. So, these work problems, they give you this formula, and they say that work is equal to force, right? And then they say times displacement. But this formula itself is extremely deceiving. A better formula to think about is work is equal to, and then you can say the integral from A to B of force density times thickness of slice. Right, so thickness of slice. Oops, running out of room here. All right, thickness of slice times variable, what's it called? Variable distance traveled. This is not working out well. Times variable distance traveled. And variable distance traveled will always be x. Well, in most cases will be x. Okay, so work is force density, so it's always going to be like, um, so like pounds per feet, something like that. Thickness of slice, that's going to be like in meters or feet. Variable distance traveled, that'll be in meters or feet. All right, so in this problem here, it's saying a chain is lying on the ground and is 10 meters long and its mass is 80 kilograms. All right, so you think of this chain that's laying on the ground like this. You have this chain that's on the ground, right? And they're telling you its total mass. Total mass is 80 kilograms. Okay, and it's 10 meters long. That's how long the whole chain is. But then they're asking how much work is required to raise one end of the chain to a height of 6 meters. Okay, so that means that not all of the chain is being lifted up. So that's kind of the same thing as lifting up a 6-meter chain like off a building, right? Because the other 4 meters of the chain are resting on the ground. So that weight doesn't really matter. What matters is the 6 meters that you're lifting. So this is very similar to a building problem. But what's deceiving is we don't have the force density. Instead, what we have is total mass. Right, we have the total mass of the chain. The chain is 80 kilograms. Okay, so we need to know what is like the kilogram per meter. All right, we need to know like what's the, not the force density just yet, but the mass density. Like for every meter, like so basically if you like, you have like a meter right here, like how much does it, what's the mass of that meter? All right, so no problem. You would just get your 80 kilograms. I think I did it over here somewhere. Where did I do it? Yeah, mass density. So you get your 80 kilograms right here, and you divide it by its length, and you get 8 kilograms per meter. Okay, so that's the mass. That's the mass density. All right, so go back over here, and if we look at our formula, it's force density times thickness of slice. Thickness of slice would always be dx times the variable distance traveled, which will most often be x. Okay, unless you're pulling up the second half of the rope, which is a different problem. Okay, so the force, all right, so we don't have force density just yet. We have mass density. So we go back down over here, got our mass density, and I put it right here into our problem. So we have mass density. Okay, what this is right here is this is acceleration due to gravity, which is 9.8 meters per second squared. That's something that you just have to know. Okay, and force equals mass times acceleration. That's why I did that. So, but this is now force density because it's not, I didn't put in like the mass of the entire thing. I put in like mass per meter, right? So I have mass per meter times acceleration. So that's going to give me basically the force per meter. That's going to give me like the force per meter. And force per meter is force density. So this is force density. All right, so we have force density, which is what we need, times dx, which is the thickness of the slice. So you're just always going to have that times variable distance traveled. Bam. Okay, from there, you're basically seeing like how much work is required to lift up like all pieces on this rope, all added up. And the reason why we have variable distance traveled is because you have like this little piece right here, and it's traveling like this distance. And then you have this little piece over here, and it's traveling this distance. So every part of the rope or chain is traveling a different distance. So that's why you have this x right here. That's variable distance traveled. If it's like one of those like second half of the rope problems, it's very different because the variable distance traveled is actually the same. But that's a different problem. Okay, so here's the setup, and the way you write it is you go from 0 to 6 because you kind of think of it as it's traveling from 0 to 6. So even though you kind of just do it like in reverse order as like the y-axis. So you have to think of it like differently, like with the spring problem, you know, you think of it horizontally and you would think of it as like from, you know, something to something, right? And it'd be in terms of a low value to a low positive number to a higher positive number. So same thing here. Because its weight or the work increases the further you go towards 6. All right, so back over here. Where is it? Here. So there's that. So oops, then you just work that out. Great. So you multiply the 8 times the 9.8 together. I took all the units out. Oh, by the way, I wrote all the individual units up here. So the 8 would have been kilogram. Oh my God, why is this moving around so much? Sorry. So the 8 is kilograms per meter, right? And the 9.8 is meters per second squared. That's acceleration. And dx, that's the thickness of the slice. That's just in meters. And x is variable distance traveled, which in meters. And if you wipe out your meters from these two left sides right here, you're going to find that everything comes out to be kilograms times meters squared per second squared, which is the unit for joule. And as a side note, the unit for, right here, oh, a Newton. A Newton is kilograms times meter over second squared, which is what this part is right here. Right, so it's kilogram hold on a sec. Kilogram, a Newton is kilogram times meters per second squared. Oh, it's this part here, right? So it's kilogram times meter per second squared. So that would be, this little piece right here is force. And this little piece right here is variable distance traveled. Okay. So, where are we? Okay. So we just multiply these two together, and we end up with 78.4 x dx. All right. And we integrate from 0 to 6. And we got 0. We have a 0 at the end, so we don't have to worry about that second part right there. And we end up with 1,411.2 joules. And that's how you do this problem. And the key to these work problems is really this: force density, thickness of slice, variable distance traveled, and knowing what this means and what this means. And in this particular problem, we had to kind of break down force density. We had to find out what force density was by using mass density, which is right here, not using the entire mass, but using mass density, and multiplying that by acceleration due to gravity, which was 9.8 meters per second squared. All right, that's it.